Hi guys, welcome to my YouTube channel, Learn Physics with IBM. Uh, Today I would like to take you to part 3 of force, density and pressure, and without wasting time, I want us to pick up from where we stopped on page in part 2. So let's straight away go to the document. In part 2, I think in part 2 we stopped on this page here. We were on page 15 and we stopped on this question here where the answer was, I think the answer was A. So I want us to continue to part 3 with the next question. So without wasting time, of course, just to remind you, the answer here was A. If you remember from part 2, you can check in part 2 if you are new to this YouTube channel. The answer was A, where we said the moment, of course, if we divide this by 2, this was 2.5, 25 and 25, that was 0.25, and this was 0.25 in meters. So the moment by 20 newtons, would be 20 times 0.25 plus the moment by 40 newtons would be 40 times 0.25, and this gave us 15 Newton meters. But we don't see 15 here. But the maximum clockwise moment should be 15. So when we say that that made B to be wrong because it says it is equivalent to clockwise torque of 20 Newton meters only. The maximum is 15. And this one is saying it is anti-clockwise. This is automatically clockwise. It can't be anti-clockwise. So it means C and D are wrong. Automatically C and D are wrong. But then what makes A to be correct yet it is 10 Newton meters. We said because they have added 20 newtons to the left, another force is added to the left. If another force is added to the left, it means it causes a clockwise moment which is going to be 20. A clockwise moment which is going to be 20 times 0.25, which gives us 5 Newton meters. No, so this will be clockwise. No, this will be because the force is to the left. X is equivalent to a clockwise torque of 10 newtons, 10 Newton meters. The total moment which is clockwise here is going to be 15 Newton meters, which is clockwise. So if there is another force to the left, then this force should cause 5 Newton meters anti-clockwise so that when 5 Newton meters is subtracted from 15 Newton meters, we get 10 Newton meters. So that makes the answer to be A. A heavy ball hanging from a cable is held in equilibrium by a chain as shown here. Which vector diagram shows the three forces acting on the ball? So there is tension in the cable, there is tension in the chain, there is weight. So I will prolong weight vertically upwards. So this will be the weight vertically upwards without changing this line for the cable. Then I will just bring the chain here. So without changing its direction, the tension in the chain should be in that direction there. So this is the chain, tension in the chain. This is tension in the cable. And this is going to be the weight of the ball. So the triangle should look something like that. So let's check here. So it means the answer is going to be A because there is weight vertically downwards, and then there's tension in the cable which points in this direction like this one here, and there is tension in the cable which points in this direction here. And because this line is making 90 degrees with this, it also makes 90 degrees with that. If that is very hard, you can also complete this parallelogram from this side, something like this, so that you see exactly. So you can see exactly that this is pointing that direction. This is 90. So this is the tension from the cable. Then this will be the tension from the chain. So it's the same thing, either this triangle here or the other one. So in the answers, they give us the second triangle, which is this one here. So our answer is going to be A automatically. First of all, because this should be forming a closed triangle for a body in equilibrium. It is just a continuous slope. It is a continuous slope. When you check this one here, this is not a continuous slope, so there's no equilibrium there. These two vectors are like this, and then the other one is the other way around, so there's no equilibrium there. There's a resultant according to the diagram. This is showing a continuous loop, but it is showing that the tension in the cable is horizontal, yet it wasn't horizontal. So the tension in the chain, this one also has changed the direction of the chain, the tension in the chain. Look at the tension in the chain, it is not in the horizontal direction. So it means our answer is going to be A. At sea level, atmospheric pressure is 10 kilopascals and density is 1.3 kilograms per meters cubed. That is at sea level. Assume that the density of air decreases linearly. Okay, if it decreases linearly, we can get the average, of course. With the height above sea level, what is an estimate of the total height of the atmosphere based on this information? So if the density decreases linearly, then the average density is going to be 1.3 plus 0 divided by 2. So if, let's say, we reach a point where the density gets to 0, so the average density is going to be that is the average density. And then we want to find the estimate total height. We know that pressure is equal to height times density times G, but this will be, we shall take the average density in this case. So the pressure is given as 100 times 10 power 3 because it's kilopascals. Is going to be equal to the height h. The average density is 1.3 divided by 2. Then G is going to be 9.81. So I'll just press my calculator to check the value of h. So I have 100 exponent 3 times 2 divided by 1.3 times 9.81. So this is giving me 15,682. 15,000, this is h, 15,682 point something. So this was in meters. This was in meters. The answers are quoted in kilometers. So it means the answer here is going to be approximately 16 kilometers. So the answer is going to be B. A uniform solid block is fully submerged in a tank. The dimensions of the block are x and y as shown in that diagram. So they've given us the dimensions. The block is held vertically in the position. The density of the block is the same as the density of the water. So the density of the block is the same as the density of the water. Okay. If the block is always held at the same depth D, below the surface of the water, which single change would increase the magnitude of the upthrust, force on the block. If the block is always held, so it means the upthrust, of course, upthrust is equal to cross-sectional area times difference in pressure. If it is fully submerged, then the height h, the height y will always be the same, even if it is even if for whatever, because d is remaining the same, then this will be cross-sectional area. Change in pressure will be density times G times the difference in height from the top and the bottom, and this will always be cross-sectional area, density G times Y, as long as it is fully submerged. So the depth D is remaining the same. The question is, which single change would increase the magnitude of the upthrust force? So you notice that the upthrust is not depending on D. It is actually depending on cross-sectional area. It is changing depending on, density and G are constants. These will not be changed. So we just look at the cross-sectional area and Y. One of them should be changing. So let's see the alternatives. Decrease the density of the block. decrease the density of the block. Of course, if we decrease the density of the block will not be the same as the density of the water, so this one will affect the upthrust. Then hold the block horizontally. Holding the block horizontally will only interchange cross-sectional area and y, because the distance x will be now in the position of y, but the cross-sectional area will be y times x. So the product still remains the same. This will not change the upthrust. Increase dimension y. When we increase dimension y, it means we change this quantity here, so the upthrust changes. So the answer is going to be C. Increase the density of the block. If we increase the density of the block, it will not be the same as the density of the water. It will actually be higher than the density of the water. But then increasing the density will affect the volume, of course. It will affect the mass, and therefore it will affect actually the cross-section area is most likely going to change. So increasing the density may decrease increasing the density may result into decreasing the volume, so there will be no change in upthrust. So the most appropriate would be increase the dimension y, because the upthrust depends on the cross-sectional area times the height y. A shelf XY is 0.4 meters long and is attached to the wall at end X. It is kept horizontal by a wire attached to Y and to the wall as shown. The tension force in the wire is 15 newtons at an angle of 30 degrees to the horizontal. What is the moment of this force about point X? We want the moment of the tension about point X. Okay. So the easiest way to do this, instead of looking for perpendicular distance, I will just resolve 15 newtons vertically upwards. And if I use 30 degrees, resolving 15 newtons vertically upwards, that will be 15 sine of 30. And I want the moment of 15 sine 30 about point X. So 15 sine 30, the tension force in the Y is 15 newtons at an angle of 30 degrees to the horizontal. What is the moment of this force about point X? So I will get 15 sine 30. That is, I think, 7.5. So the moment, I will use TAR for torque, or moment is going to be, I think this is 7.5 newtons. So 7.5 newtons is 15 sine 30 times now the perpendicular distance, which is 0.40. And when you press your calculator, 7.5 times 0.40, that gives us 3 Newton meters. So it means the answer here is going to be A. A statement about the principle of moments with some words omitted is shown in the figure. For an object in a state of rotational equilibrium, here this means no resultant moment, the sum of the clockwise moments about n point is equal to the sum of the anticlockwise moments about, this should be about the same point. This should be about the same point. The sum of clockwise moments about n point is equal to the sum of anticlockwise moments about the same point. So the question is, which words correctly complete the statement? Of course, this is automatically D, same point. A bird dives to a depth of 1.5 meters below the surface of a lake. Atmospheric pressure is 101 kilopascals. The density of water is 1000 kilograms per meter cubed. What is the pressure at this depth? So one pressure. So of course, pressure at a given depth is going to be pressure due to the atmosphere plus the pressure due to the depth. So that is pressure due to the depth is given as density times H times G. So this will be atmospheric pressure, that is 101 times 10 power 3 to change it to pascals, plus the density is 1000 times the depth is 1.5, then times G, which is 9.81. So we shall check our calculator. So I'll start with 1000 times 1.5 times 9.81 then plus 101 exponent 3. So this gives me a 1157, which is approximately 116. So this is approximately 116 kilopascals. So the answer is going to be D. A cylindrical block of wood has cross-sectional area A and weight W. Cross-section area is A, weight is W. It is totally immersed in water with its axis vertical. The block experiences pressure PT and PB at its top and bottom surfaces respectively. What's the upthrust? I've been saying upthrust is given by cross-sectional area times difference in pressure. So the difference in pressure is the pressure at the bottom minus the pressure at the top, because the pressure at the bottom is greater. So this would be the cross-sectional area into pressure at the bottom minus pressure at the top. So this means our answer is going to be B. Pressure at the bottom, because pressure increases with the depth, pressure at the bottom is greater than pressure at the top. So the answer is going to be B. Pressure at the bottom minus pressure at the top times cross-sectional area. Number next, two forces, each of magnitude F, act on a disk of diameter S as shown in the figure here. What is the torque exerted by the disk? Of course, if I have two forces that are equal and opposite, then the torque, which is the moment of a couple in this case, is going to be the product of one of the forces times the perpendicular distance between the two forces. Product of one of the forces times the perpendicular distance between the two forces, which makes the answer to be C. A mass of 500 grams is attached to at one end of a rod of length 1.5 meters. The rod is pivoted at the distance of 25 centimeters from the other end. The rod is horizontal. The rod is horizontal. What is the moment above the pivot due to the mass? So this is the pivot. We want the moment about the pivot due to this mass. We just need this perpendicular distance here, which will be 1.5 meters minus, I think this is 0.25. So this perpendicular distance is 1.5 minus 0.25 in meters. So we want the moment above the pivot caused by this mass. So the moment, which is the torque, is the product of the force. So this force here, because this is 0.5 grams times G, kilograms times G, which is 9.81. So the force is 0.5 times 9.81. So we have 0.5 times 9.81, that is the force due to this mass, times the perpendicular distance. And the perpendicular distance is 1.5 minus 0.25. So what is this moment? Let's check with the calculator. I will simply say 1.5 minus 0.25. Then I multiply by 0.5 times 9.81. So this is giving me a 6.1. So this is 6.1 Newton meters, which makes the answer to be C. A beam QR is held in position by a wire PQ. The structure is used to form a crane supporting a stationary load of 4 kilonewtons as shown in the diagram. Okay, before reading the question, we can try to find the forces which are acting here. Number one, there is a force from this which is in this direction here. There is a force in this which is the tension. And I'll call this force F. I'll do a vertical line here. And if this, I think this angle here, if you look at it very carefully, if you make this horizontal, this is 30 degrees and this is 60 degrees. Okay, let's see the question. What is the force exerted by the beam QR on point Q? So we want the force from exerted by the beam QR at this point Q. That force, I've called it F. Of course, it points in that direction. It's like a reaction force. Okay. So to begin with, because this is in equilibrium, so I'm going to consider equilibrium. And if I try to consider equilibrium, resolving f vertically upwards, it is going to be f. I think that would be f cos 60. And resolving f horizontally, I think that would be f. Resolving f horizontally, let me use, which angle should I use? Okay, let me use 60. So this will be f sine of 60 if I use the angle 60 degrees. If I take it upwards, this would be f. So f sine, let me use a different color for resolving so that people can see I'm resolving. Resolving f to the horizontal using 60 to be f sine 60. If you want to use 30, it will be f cos 30. Then resolving f upwards, it will be f cos 60. Of course, if you use 30, it will be f sine of 30. And I think I should take, I just get the resultant here. So considering the vertical, f cos of 60 is probably equal to k, which is going to be 4,000. I mean, is equal to 4 kilonewtons, which is 4,000 newtons. And if I resolve, if I consider f in the horizontal, then f sine of 60 is going to be equal to t. F sine 60 is going to be equal to t. Okay, so let's try to solve these two equations because I want to find the force exerted. I want to find the force exerted by the beam QR on point Q. So I have to combine these two equations here. But the easiest way to do this, let me see the easiest way to do this without okay. I didn't want to find T, but I'm going to be forced to find T anyway. Okay, so I'm dividing the two equations. So I have that tan of 60 is equal to T over 4,000. So it means T is going to be 4,000 tan of 60. I didn't want to find the T first. So if T is that, then I'll go back in any equation which has F and substitute for T. So it means F sine 60 should be equal to T, which is 4,000 tan 60, 4,000 tan of 60. Then I divide this by sine 60, divide by sine 60 to get, I divide by sine 60 to get F alone. So this cancels this side. So I'm just going to press my calculator, 4,000 tan of 60, then divide by sine of 60. So this is giving me 8,000 newtons. So F is 8,000 newtons. F is equal to 8,000 newtons. If you're more experienced with this, you would have resolved the T in the direction of this one here. So it points this side. When I resolve T in this direction, I think it would be T cos of 30. That would be T cos of 30. And for equilibrium, T cos 30 should be equal to F. For equilibrium, so sorry, I'm resolving T cos 30 along this. I could also resolve this in the same direction. So that would be T, resolving this will also point to this side. It will be T, 4,000. That would be 4,000. If I use this angle, which is 60, that will be 4,000 cos of 60. So I would say T cos 30 plus 4,000 cos of 60. should give us F. I've resolved the two forces in the direction along the same line as F. So T in that direction is T cos 30 if I use this angle. Then if I resolve 4 kilonewtons in this direction to be 4 cos of 60, this should give us the force pointing away. You can check this. But also I know that F cos 30 is equal to T. That is, if I resolve F in the horizontal using 30, it will be F cos of 30. So F cos 30 should be equal to T in the horizontal. So I can now substitute for this. I could just go and substitute for this, so that where there is T, I put F cos 30, so it becomes F cos squared 30 plus 4000 cos of 60 should be equal to F. So there's a common factor here, so I just try to solve for F here. And if you try to solve for F, I'm very certain you'll still get the same thing. Let me check. So cos 30 squared, so that is cos of 30, but squared, that is 1.5, sorry, 0.75. So I'm going to take it the other side. So I will say 1 minus 0.5 because I'm taking this one the other side. So this is 0.5f, taking it the other side. I have f minus 0.75f should be equal to 4000 cos of 60. So what is f? I'll just check f. So 1 minus the answer, that is 0.25. Then I have 4000 cos 60 divided by the answer. 4000 cos of 60 divided by the answer, which is 0.25. That is 8000. So F is still 8000 newtons. So you notice that I resolved T along the direction of F, or parallel to F, so that I could simply equate the sum of T and the weight downwards of 4 kilonewtons to F. So it gave me the same answer. So I think our answer is going to be 80 kilonewtons. That is D. A metal cylinder totally immersed in water is hung from a Newton meter. Okay. The cylinder of height L is slowly raised vertically by lifting the Newton meter. Okay. Of course, before it reaches this surface here, the upthrust will not be changing because the upthrust is equal to the cross-sectional area times difference in pressure, which is equal to the cross-sectional area density times G. Difference in height, this will simply be L. This will always be L until it reaches here. So this will be times difference in height at the top and the bottom of the object. So this part here is L. Before it reaches the surface of water, the upthrust remains the same. Okay. As the base of the cylinder moves from line X in the water to line Y above the surface of the water, the reading R on the Newton meter is recorded. The velocity of the cylinder is constant. So it means the dragger force is not actually the dragger force is not changing. Which graph best shows the variation of R with the distance d of the base of the cylinder from line X? So initially, for all of them, remember the upthrust should first remain constant. So it is initially constant. So the resultant force, because we are looking for the resultant force, is going to be the reading on the Newton meter. So the resultant force R should be equal to the weight vertically downwards minus the upthrust. So initially the weight is not changing and upthrust is not changing before we reach the surface. So it means the R remains constant throughout. So B is automatically disqualified. A is automatically disqualified because they are showing that R increases initially. Even this one is showing R increases. Okay. Then after when we reach the surface, upthrust is going to depend on the R. So R is going to be equal to W minus the upthrust, which is going to be cross-sectional area, density, G, where there is H, I'm putting L, but L is going to start decreasing. The height which is submerged is going to start decreasing. So as we reach L, because L starts decreasing, when L starts decreasing, this part here becomes smaller, the difference becomes bigger, so R increases. So it means as we move out, L starts decreasing, the height submerged starts decreasing, the upthrust reduces. So it means this R increases. So R should be increasing at that point, but then the increase is going to be uniform because L decreases uniformly, so W minus that upthrust decreases uniformly. Increases uniformly, so this should be a straight line, not a curve. So the answer is going to be C. So at L, this should be a straight line because R increases uniformly as L decreases uniformly. So the answer is going to be C. So I have said L decreases, and because the weight does not change, the upthrust decreases. So if the upthrust decreases, the resultant increases. That's why we are having a straight line here. If of course in air, when we reach air now, if the whole all the of course after it is going to be in air, then in air is going to be the same. So again the upthrust remains constant. Now in air, this was after coming out of the water, then in air R is going to be the weight minus the upthrust. Because air is going to be the same, then the upthrust remains the same, the weight remains the same, so R will be the same. So after coming out, this should be constant. That's why we have a horizontal line again. So the answer is going to be automatically C. But I want you to note that the upthrust is the same, but it is going to remain constant, but it's not the same in magnitude as that we started with, because upthrust also depends on density. The density of air is less than that of the liquid. So that's why you see the upthrust here remains constant in air, but is smaller than the upthrust we had before, because here we were in a liquid. So this part here, R is going to be bigger than for this part here, where R is going to be smaller since the upthrust was bigger when we were still in water. So the answer is C. Spherical objects fall through water at a constant speed. Three forces act on the object. Which diagram showing these three forces to scale is correct? Which diagram showing these three forces to scale is correct? Okay. So a spherical object falls through water at a constant speed. Okay, so the resultant force should be 0. That means forces acting in the opposite directions should be cancelling out. First of all the vertical lines downwards are the same, and these are representing the weight. So this is the weight, and this is going to be wrong because when I add this to this, it will be greater than the weight. So this is going to be giving a resultant. You notice that this length here, you can try to measure. That length here, when I add this one, it will be greater than this length for the weight. So that one will be out. Then because it is falling by the way, of course, it makes sense to see that the upthrust is upwards. And of course, since it is falling downwards, there is also the dragger force, which is also going to be upwards, since it is going down. So these two must be acting upwards. But one of them remains constant throughout. As long as it is still in the liquid, it is fully submerged, the upthrust does not change. It's only the dragger force which goes on changing. So this one is showing, of course, this one is going to be wrong. When you combine these two, you don't get the weight. So this one is out. And this one is showing that one of the forces Of course, this is automatically wrong because when you combine these two, you don't get the weight. So most probably the answer is B, that when you measure this length, you add it to this one, you most likely get the length downwards. So the answer is going to be B because the resultant force should be 0. So the answer is B. Two forces act as a couple. Remember, a couple refers to two equal forces whose lines of action never meet. Their lines of action never meet, they are parallel to each other, they are equal in magnitude. Which statement about the two forces must not be correct? Not be correct. They act along the same straight line. Not at all, because this would mean their lines of action are meeting. I think they act in opposite directions. They are of the same type. They have the same magnitude. So they are equal but opposite. So the answer is A, not correct. A sign outside a shop is suspended from a rusty horizontal hinge at its top end. The sign hangs in equilibrium at an angle of 25 degrees to the vertical as shown. The sign is a square of side length 52 centimeters and uniform thickness. It has a mass of 36 kilograms. It has a mass of 36 kilograms. What is the moment of the weight of the sign about the hinge? We want the moment about the hinge here. So assuming this sign is uniform, let's say its weight is acting at the midpoint. And because it has a mass of 36 kilograms, its weight is going to be 36 times g, which is 9.81 newtons. So want the moment of the weight of the sign about the hinge. So I just need the length, because the sign is a square of side length 52 centimeters. It is a square of side length 52 centimeters. So since it is a square, then I will need the perpendicular distance from the line of action. So the perpendicular, this is what I have, something like this. I'm looking, remember this is the direction of the weight, and this is the direction of, this is the length of the sign. Of course, I don't need this distance here. This is the sign post. I only need this distance, which makes 90 degrees with the line of action of the weight. And of course, this distance, if this angle here is, what was this angle? I think this angle is 25. So this angle is 25 degrees. So if you're good at maths, opposite this length should be half, because of it is 52, that is 26 centimeters. From here to this point here, so this is 26 centimeters. So it means that is 0.2. So it means D is going to be equal to 0.26. That is perpendicular distance times sine, that is opposite hypotenuse, that is sine. So that is times sine of 25. That is D. So let's find the moment. So the moment is the torque, which is a product of the force, that is 36 times 9.81, then times the perpendicular distance, which is 0.26 sine of 25. So I'll check with my calculator. 36 times 9.81 times 0.26 sine of 25. So that gives me 38.8, which is approximately 39 Newton meters. So the answer here is going to be A. A uniform rod of length 200 centimeters is freely pivoted at point P. The rod is held horizontally in equilibrium by a 60 Newton weight that is attached to the rod by a string passing over a frictionless pulley. Okay, what is the weight of the rod? Of course, if this pulls downwards by 60 newtons, the tension here in this direction is going to be 60 newtons for equilibrium. So as a mathematician, you could resolve this vertically upwards if you want to easily tell the perpendicular distance from the point P. So you want to find the weight of the rod. What is the weight of the rod? Of course, the weight of the rod must be acting at its midpoint since the rod is uniform. So let's say the weight is here. I'll call this W. Since it is 200 centimeters, from one end to the center is 100, so this distance is 60 centimeters. And the distance of the tension, which I'm going to resolve, tension 60 newtons, resolving upwards will be 60. Using 30 degrees, that will be 60 sine of 30. And its perpendicular distance from the point where I'm taking moments is 200 minus 40, that is 160 centimeters. Okay, so for equilibrium, the resultant force should be 0, the resultant torque should be 0. Okay, so it means the weight W times the perpendicular distance from the point I'm taking moments. The perpendicular distance is 60, so that is 0.6 should be equal. This is the only force causing clockwise moment. The tension is causing anti-clockwise moment. So this would be 60 sine of 30. 60 sine of 30, that is the force, times the perpendicular distance, which is 160 centimeters, that is 1.6. So I'll just check my calculator and find W. So 60 sine 30, I think that is still 30. 60 sine 30, that is 30 times 1.6. Then divide by 0.6, that is 80. So W, which is the weight, is equal to 80 newtons. So my answer is going to be C. The diagrams show two blocks X and Y. Block X has sides of length A. When block X is placed in a liquid of density rho with the shaded face level with the liquid surface, it experiences an upthrust U. So let's see the upthrust. This side is, remember, upthrust is cross-sectional area times difference in pressure. That is cross-sectional area times density times G times difference in height. So the upthrust this side, which is U, is the cross-sectional area, which is A times A, that is A squared, times density, which is rho, times G. Then the height is also A, so this is A. So this is A cubed times density times G, that is U. Block Y has horizontal sides of length A and 2A and height half A. Block Y is placed in a liquid of density twice rho, also with the shaded face level with the liquid surface. What is the upthrust of block Y? So block Y has upthrust U, which is cross-sectional area, it is 2A. The cross-sectional area is 2A times a half A. So I'll say cross-sectional area is, no, this side is A, so it is 2A times A, so that is 2A squared, that is the cross-sectional area, times the density is twice rho, times G, times the height, which is a half A. So the height is a half A, so the 2 can cancel with that one. So 2, we have 2A squared times A, that is 2A cubed times density times G. So notice that this is twice the other one, so the answer is going to be twice U. So this is twice, this is upthrust for Y. The other one was upthrust for X, so this is twice U. So the answer is C. A gas is contained inside a syringe as shown. The initial volume of the gas is 2 centimeters cubed. Atmospheric pressure is 101 kilopascals. What is the work done by the gas of the atmosphere when the gas is heated and expands to a volume of 6 centimeters? Of course, we know that work done is equal to pressure times change in volume. So the pressure is 101 times 10 power 3. The change in volume changes from 2 to 6. So the change in volume is 6 minus 2, but this should be changed to meters cubed. So it is times 10 power. Changing it to meters cubed. Okay, let me leave the answers in, let me leave it in centimeters because I could be having, okay, this is going to be times 10 power minus 6 to change it to meters cubed. So this is going to be equal to 40, I think, 101 times 4. That is 404 times 10 power minus 3. This is in joules. Of course, minus 3 is millijoules, so the answer is going to be B. That is 404 millijoules. A ball falls through a liquid at constant speed. It is acted upon by three forces: an upthrust, a drag force, and its weight. Which statement is correct? So on 1, the weight is going to be constant. The weight should be constant. And the upthrust is equal to cross-sectional area times difference in pressure, which is equal to cross-sectional area times density times g times difference in height, which is just the height, the length of the object, or the difference between the top and the bottom. If it is fully submerged, the height, the upthrust is also constant. So weight constant, upthrust constant. But if the speed is constant, then the drag force also will remain constant because the drag force depends on the speed. So let's check. The drag force increases with the speed, with the depth. No, the drag force depends on speed. Friction depends on speed. In friction in a medium, or resistance in a medium depends on the speed, just like air resistance increases as you speed up. So the drag force would increase if the speed was not constant. If the depth is increasing and the speed is not constant, the drag force would increase, but the speed is constant. The drag force is equal to the sum of the upthrust and the weight. So the upthrust is upwards plus the drag force, which is upwards, should be equal to the weight. So this statement is not correct. For an object falling, upthrust is upwards, the drag force is upwards, the weight is downwards. So this statement is not correct. The upthrust is constant with increasing depth. The upthrust depends on the difference between the top and the bottom. If it is fully submerged, this distance is remaining the same, so the upthrust is constant. So the answer is going to be C. The weight is greater than the sum of the drag force and the upthrust. Not at all. The weight should be equal to. If it is moving with a constant speed, the acceleration is 0. Constant speed, acceleration is 0. Resultant force is 0. So it means the weight should be equal to the sum of the upthrust and the drag force. So the answer is C. A fairground ride consists of 4 carriages connected to a central vertical pole as shown in the diagram. A motor rotates the central pole about its axis. This results in the 4 carriages each moving along a circular path. The distance from the middle of each carriage to the center of the pole is 3.20 meters. When they are moving, each carriage experiences an air resistance of 85.0 newtons. Assume that there are no other significant resistive forces. Which torque does the motor need to apply to the pole to keep the system rotating at constant maximum speed? Which torque? Okay, so we have something like this. We shall have something like this here, and it is rotating in that direction. So these are the torque is going to be equal to the force times perpendicular distance. So I'll just consider 2 forces. So 2 equal but opposite forces, then I'll multiply by 2. So this one and this one constitute, of course, these ones, the lines of action. No, let me just find the resultant moment. The resultant moment. So if they are rotating clockwise, the torque due to 1 is going to be the, let me see, okay, assume that there are no other significant resistive forces. The distance from the middle of each carriage to the center, okay, the distance is 3.2. Okay, so the torque on each carriage should be 8, 5 times 3.2. then times this is going to be multiplied by 2, and I'll again multiply this by 2 because this is the torque on one carriage, but then there are two, and then so that is the torque due to 2 is going to be 85 times 3.2 times 2. Then the torque due to the other two should also be, I just multiply that by 2. So that means it's like multiplying 85 times 3.2 times 4. So this is going to be 85 times 3.2 times 4, which gives me 1088. 1088. So this is going to be the resultant torque due to air resistance. So the question is, which torque does the motor need to apply to the pole to keep the system rotating at a constant maximum speed? So if this is the resultant torque due to air resistance, then this torque, an equal but opposite torque, or an equal torque should be exerted to overcome the air resistance. Therefore, the answer here is going to be D. That is 1090 Newton meters. So the answer is D. A uniform horizontal beam or X, 4 meters long, it's 4 meters long, and weighing 100 newtons is hinged at a wall at point O. It is supported by a cord XY which is attached to the wall at Y. What is the tension in the cord? What is the tension in the cord? So tension, of course, will point that direction. Because this beam is uniform, its weight acts at the midpoint. That is, this is 2 meters, this is 2 meters. So the weight is 100 newtons. So we want the tension. So I will resolve this vertically upwards for easy calculation. For easy finding of the perpendicular distance, taking t to the vertical will be t sine of 30. T sine of 30. So because there is equilibrium, if there is equilibrium, then the resultant moment should be 0. Alternatively, I will just look at t sine of 30 times its perpendicular distance, which is 4 meters. This will be causing anticlockwise moment, and the weight will be causing clockwise moment. So this should be equal to 100 newtons times the perpendicular distance of the weight, which is 2. So I'll just check with my calculator. That is 200 divided by 4 sine of 30. So that means T is 100 newtons. So the answer is going to be D. An object shaped as a hemisphere rests with its flat surface on a table. The object has radius r and density rho. The volume of a sphere is 4/3 pi r cubed. Which average pressure does the object exert on the table? Which average pressure does the object exert on the table? Okay. So this is a hemisphere. So it's only that is drawn like this. People cannot see. Uh, maybe I could add another circular part at the bottom, which is bigger, so that people can see that it has a circular sphere. So the cross-section area here of this part here, the cross-section area is going to be, the cross-section area is, okay, which average pressure does the object exert on the table? The cross-section area is a circular path. So area is going to be pi r squared. The cross-section area is pi r squared. So if I want to find pressure, pressure should be equal to the force over area, which is going to be the weight, over area, which weight will be mg, over area, which mass is density times volume. So this will be density times volume times g over the area. But density volume is 4/3 pi r cubed. So the pressure will be equal to the density times volume, which is 4/3 pi r cubed. That is the volume, times g divided by the area, which is pi r squared. So pi cancels out, r squared cancels with that, and literally I remain with The density is rho, the radius is r. No, this is a hemisphere, so the volume is half. So I'll divide this by 2. The volume of a sphere is that. For a hemisphere, it is divided by 2, so this is going to be 2 over 3. 2 over 3, not 4 over 3. Because it's a hemisphere, I divide by 2. So this becomes 2 over 3 times density times r times g. Is that true? Which average? Okay, so that is true. 2 over 3 times density times r times g. So the answer will be D. Since it is a hemisphere, it is half a sphere. So I divide the volume by 2. So that is 2 over 3 pi r cubed. Okay, the answer is D. A uniform rod of weight 20 newtons and length 2 meters is acted upon by 2 vertical forces as shown. So this is causing a clockwise moment. This is causing an anti-clockwise moment. What is the resultant force? The resultant force is 15 plus 5, which is 20. So we ignore A and B. Then the resultant moment. The 15 causes clockwise moment. So a uniform rod of weight 20 newtons. Sorry. So the weight of this should be acting downwards 20 newtons. So that is wrong. This is not true. Because the weight is 20 newtons, it is uniform. The weight is acting at the center. This is 1 meter. This is also 1 meter. The resultant force is 0, so ignore C and D. Okay. Then a moment. What is the resultant force acting on the rod and the resultant moment about the center? 20 newtons will have no moment if we take moments about the center. 15 newtons causes 15 times 1 about the center, that is clockwise, minus 5 newtons causes 5 times 1, which makes the resultant to be 10 newton meters. So the answer is going to be A. No resultant force because total force upwards is 15, total force downwards is 20 newtons. Okay, so this should be the last question in part 3. 3 coplanar forces act on a block. Which diagram shows the direction of the forces such that the block could be in equilibrium? Which diagram shows the directions of the forces such that the block could be in equilibrium? So if I have 3 forces, if they are joined head to tail, they should form a closed triangle. So let's try to forge triangles here. These ones will never form a closed triangle. You can't join. These ones will not form a closed triangle. So D is automatically out. They will never form a closed triangle. Then we can check. If I begin from this one and on its head I add the weight vertically downwards, then bring this vector here, it is nearly impossible to join the head, this one here, to form a closed triangle. This one can never be joined to form a closed triangle. So this triangle will never be closed. So this one means there is a resultant. So this is out. If I fix the vertical vector in that direction, I add this one in that direction. Then when I look at this one here, when I add this one here, of course, I'm trying to put in a concept of magnitude. When I bring this vector on the head of the other one, I think it will be a vector here. This one could form a closed triangle. Let's check A. If I fix the horizontal vector and I add this vector here, then comparing the magnitudes, this could form also, let me see, points out downwards. So you have to choose between A and B. So now here, if you have a ruler, you can check the magnitudes. You check the magnitudes, you join with the magnitudes, measure the magnitudes and draw a closed triangle and check if you get a closed triangle, but most likely the answer is going to be B. From my judgment, I think the answer is going to be B, because these ones are also forming a closed triangle when you join head to tail. These ones are also forming a closed triangle when you join head to tail. But most likely, when I look at the magnitude from my judgments, I think the answer is B. However, you can measure the lengths using a ruler as you form the triangle and see if the triangle will be perfectly closed. Okay. The other way of looking at this, suppose I prolong this vertically downwards and I prolong this. I wish I had a ruler. Let me try this. So get a ruler, prolong the forces and see where they meet, if they meet at the same point. So I take this one downwards. Okay, take this one downwards and bring this one downwards. If they meet, then that means they are in equilibrium. Try to prolong these ones also and see. If I take this one longer, take this one vertically, prolong this, these ones will not meet at the same point. So these ones will not form, these ones are not going to give us equilibrium. So these ones, if you prolong them, these ones of course will never meet at the same point. So the other way to look at it is by prolonging these ones, this vector. If they meet at the same point, that means they're acting on a body in equilibrium. Okay, let part 1 stop there. Let part 1 stop there. I said here the answer, part 3 stop there. The answer there is B. See you in part 4. Bye bye.